Hello friends, let us now learn some important points about the new phosphor technology. So, it is usually agreed that maximum useful speed of calcium tungstate screens is already achieved. The new phosphor screens have permitted greater speed, but this changing technology is complex and it is perplexing. So, ways to increase the screen speed. So, there are three major ways to increase screen speed. That is one, we can use a thicker phosphor layer. Number two, we can use a higher conversion efficiency phosphors. Number three, higher absorption phosphors. So, first, we must consider how an intensifying screen speed can be increased. This can be done when the phosphor layer can be made thicker to absorb more of the X-ray beam, like the thicker phosphor layer. The phosphor may have higher conversion efficiency of X-rays to light, or the phosphor may be able to absorb the X-ray beam effectively. So, a thicker phosphor layers absorb more of the X-ray beam than the thinner phosphor layers. The major way in which the speed of calcium tungstate is increased is by thicker phosphor layer. A pair of DuPont par speed calcium tungstate absorbs around 20% of X-ray beam, whereas a pair of DuPont high plus screens will absorb around 40% of X-ray beams. So these high plus screens are not twice as thick as par screens. They are 2.3 times as thick as par screens. Why is this? When the amount of X-ray absorption is doubled, why is the thickness of the DuPont high plus screens more than double when compared to DuPont par speed screens? So for this we have to take an example. For example, if this is a par speed screen and if 100 photons or 100 X-ray photons struck a pair of par speed screens, so among this 100 photons 20% is absorbed by calcium tungstate screens. So with a par speed screen, the X-ray photons 20% are absorbed, that is 20 X-ray photons are absorbed, whereas 80 X-ray photons will pass through a second par speed screen. So, a second set of par speed screen is placed in the path of this 80 X-ray photons. So, this second par speed screen also absorbs 20% of X-ray photons. 20% of 80 X-ray photons is around 16. So, that means 16 X-ray photons are absorbed. Remaining 64 X-ray photons will pass through the par speed screen. So here this is not double actually. So the double thickness of far speed screens absorbs only 36% of the X-ray beam rather than 40% of the X-ray beam. So as a result, the DuPont high plus screens, in order to absorb 40% of X-ray beams, they should be around 2.3 times as thick as the far speed screens. So it is possible to continue increase in the calcium tungstate screens by increasing the screen thickness, but the main disadvantage is due to the unsharpness of the image. So but unsharpness of image is caused by the light diffusion in the thick phosphor layer and it is unacceptable. In calcium tungstate screens, a compromise should be made between the speed and the sharpness. So the second way is high conversion efficiency phosphors. So in high conversion efficiency phosphors in 1972, reports describing rare earth oxysulfide phosphors for the use of intensifying screens were published. This work was supported by a contact from Atomic Energy Commission of to the Lockheed Corporation, and this class of phosphors is sometimes referred to as Lockheed rare earth phosphors. These rare earth phosphors have been commercially available since 1973. The chemists divide the periodic table into four basic groups: alkaline earths, rare earth elements, transition elements, and non-metal elements. The rare earth elements developed because these elements are different, are difficult and expensive to separate from the earth and each other. These are not because these rare earth elements are not scarce, but these elements are difficult and expensive to separate from the earth and from each other. So these rare earth groups consists of elements of atomic number 57, that is lanthanum, through atomic number 71, that is lutetium. So it includes atomic numbers 57 from lanthanum to atomic number 71, that is lutetium. So this includes thulium 69, terbium 65, gadolinium 64, europium 63, and lanthanum is the first element and of the rare earth group. So thus these whole series are called as lanthanide series. So lanthanum and gadolinium are used in the rare earth phosphors. A related phosphor called yttrium with an atomic number of 39 is not a rare earth phosphor but has properties which are similar to those of these rare earth phosphors. These rare earth phosphors are mainly produced as crystalline powders of terbium activated gadolinium oxysulfide. They are produced as crystalline powders of terbium activated gadolinium oxysulfide and thulium activated lanthanum oxybromide. So unlike calcium tungstate, the rare earth phosphors, these do not fluorescent properly in a pure state. They do not fluorescent properly in pure state. For example, the maximum fluorescence of gadolinium oxysulfide, terbium activated gadolinium oxysulfide, is around 0.3% of gadolinium are replaced by terbium. So the fluorescence of gadolinium oxysulfide occurs when 0.3% of gadolinium atoms are replaced by terbium. So this impurity is responsible for the fluorescence of the rare earth phosphors. So the X-ray to light conversion efficiency of rare earth phosphors is slightly greater than calcium tungstate. So if you see in general, generally to state that X-ray to light conversion efficiency of calcium phosphate is 5%, whereas the X-ray to light conversion efficiency of these rare earth phosphors is 20%. So we can state that one X-ray photon in calcium tungstate intensifying screen will produce 1000 light photons, and these same one X-ray photon absorbed by these rare earth phosphors will produce around 4000 light photons. So the conversion efficiency of yttrium oxysulfide screens is almost same as gadolinium oxysulfide. So if you see this rare earth phosphors, thorium at the X-ray to light conversion efficiency of thorium activated lanthanum oxybromide is 18%. Then terbium activated gadolinium oxysulfide is also 18%. Then terbium activated yttrium oxysulfide is also 18%. So these major rare earth elements have the X-ray to light conversion efficiency of around 18%. Then there is a fairly new addition to the family of rare earth screens are rare earth tantalates. So these rare earth tantalates have a generic formula of lanthanum tantalate, which is LnTaO4. This Ln can be any lanthanide series. These are tantalate phosphors. These tantalate phosphors can be made up of most of the lanthanides, but commercially available screens have made use of yttrium tantalate. So this yttrium tantalate is available commercially. Then we have some rare earth intensifying screens. So if you see the table, we will see some of the examples of rare earth intensifying screens commercially. First, DuPont. The name is Chronex Quanta 3. Chronex Quanta 3 contains lanthanum oxybromide, thulium activated, and it emits blue spectrum. Then Quanta Detail contains yttrium tantalate, thulium activated, emitting the ultraviolet or blue light. Quanta fast detail contains yttrium tantalate, niobium activated, yttrium tantalate, niobium activated, emitting the ultraviolet blue light. Then Chronex Quanta 5. Then the next name is Chronex Quanta 5. Contains lanthanum oxybromide, thulium activated plus gadolinium oxysulfide, terbium activated. So because both of these will produce almost two spectrum of wavelength, that is, it produces blue colored wavelength and green colored spectrum. Then the next manufacturer is Kodak. Kodak manufactures X-osmotic fine. This X-osmotic fine contains barium lead sulfate, which is yellow dye, and it will absorb blue wavelength. Then X-osmotic regular contains barium strontium sulfate, europium activated neutral dye, which emits blue wavelength. Then Lennox 5 contains gadolinium oxysulfide, which is terbium activated neutral dye, and this is emits green color. Whereas Lennox medium contains gadolinium oxysulfide, the same terbium activated, but this is yellow dye. Gadolinium oxysulfide, terbium activated, containing yellow dye, and this also emits green spectrum. Whereas Lennox regular, it is gadolinium oxysulfide, terbium activated, which also produces green dye. So here there are two tantalate screens are also. So there are some two tantalate screens which are also manufactured by DuPont manufacturer, which is yttrium tantalate, which is thulium activated, contains yttrium ions replaced by thulium. Similarly, yttrium tantalate niobium activated, some of the tantalate ions are replaced by niobium. So this yttrium activated niobium niobium activated yttrium tantalate has a conversion X-ray to light conversion efficiency of 11%. Thank you.